Okay, so next section is the first order linear differential equations. Okay, so recall that the what we call a differential equations is any equation uh, containing derivative f in its terms. Okay, order is the highest derivative order. So first order differential equations means that it's only first derivative, no second derivative, no third derivative or higher, only first derivative. Linear I'll explain later on what linear means. Okay. Okay, so far what we do with the first order differential equations is to separate the variables, one in left hand side and the other on the right hand side. Okay, such that this is separable. Let's see. Linear first order differential equations. Okay. So this is separable. Say this one here. Separable because you can write this down. A, B, T. That's this is containing T, and here containing K. Sorry, T. T. Okay, so this means separate variables. Here's T and T. Right. All right, so this is non-separable. And this is so say this one here, dy dx to x minus 3y. So this one here. So there's no way you can put y in one side and x on the other side. Okay. If this is a multiplicative form, so x times y, then it is possible, but this is a plus. Okay. There's no way to separate. There is no way to separate x and y. Okay, so this is non-separable. So how to do this non-separable thing? All right, so this is the trick. So we'll do with the differential equation called B of the form first one. This in general, dy dx p of x times q of x. Okay, so this is the okay. So let's see. just name. If x equals 0, then it's called the homogeneous. Homogeneous. Non-zero, then it's called non-homogeneous. Okay, so we separate those two cases, homogeneous uh, and non-homogeneous. Okay, so how we solve this one here? Okay, let's see. Okay, so we have the terms general solutions and initial conditions and particular solutions. Okay, so usually we have differential. This is the dE, dy dt, sorry, dy dx. This px of okay. This is the dE. This is initial conditions, usually. So there usually comes in a couple. Okay. So then the objective is find y of x. Okay. Okay, so let's give me an example. Work. So how to solve this one here? Okay, there's a little trick here that um, we multiply both sides by this one called integrating factor. Okay, so what's the reason of multiplying by this a kind of strange looking term into integral px? Okay, so let's do this one. Integrate the negative dx dx. All right, so let's do the one example. And the reason for this is, let's see, dy dx is multiply by e to the x, right? And 2x times e to the all right, so you see that the reason is this one here. If you think about this one, so dy dx times e to the and dx y. It's okay. So recall what is the dx of e to the integral px. When you take derivative of this, right? So what you get here? So again, you get into this exponential, exactly the same thing, times the, because the chain rule, times the derivative of this integral. Okay, but in derivative of this integral, that will makes the disappear. Okay, so you have a constant, but uh, no, you don't have the constant. Sorry. So this is just px. Okay. So then think about, so I better write this down as this y times. Okay. So this is actually the derivative of this one. Okay. So this remains the same. Okay. So what I'm saying is that this is the form of y prime e to the plus y times there. Okay. So can you recognize what is the left-hand side? What's the left-hand side here?
Derivative of multiplication.
Multiplication. So this is the product rule. So this is the dpx of y times e to the there. Okay. So in order to solve this, to get this, just do the integrations. So what we have is just integrate. Okay. And you get this integral. A little bit nasty in the form, but in computations, it's okay actually. Yeah. Okay. So then y is, well, this is just multiply with e, right? So times this integral. Okay, so we get this solutions. Okay. And the thing is, you don't have to memorize the formula. It's nasty formula. Don't try to memorize this one. Just what you need to remember is this form over here. This is what you need. Okay, and the step how to do this one. But just don't try to memorize this formula here. Okay, so just example. Okay, let's just do example in the book here. Okay. So from the problem here, we recognize that the uh, this is p of x, right? This is Q of X. So, so the integration factor is now e to the negative P of X dx. Okay. Sorry. So integral P of X is integral of X dx. So this is ln of C. Okay. So we pick something that the easiest. Pick the one that easiest. Easiest. That is C equals 0. So then you integration factor is 2 ln of x. Or you can say this is ln of x squared. Okay. Right. And you can assume this is a x positive, so then you can get rid of the absolute value. All right, so let's multiply the equations by integration factor. So you get dy dx plus 2 over x times y equals sine 3x over x squared. Oh, sorry. The integration factor should be e to the is e to the here 2 on x. So e to the ln x squared. E then ln cancel out. So you get just x squared. Okay, so this is the integration factor. So you multiply this by x squared. So what you get here? So this is a, let's see. This is dy dx over x squared plus this is so 2x 1. Okay. And here you get x squared cancel. Okay. Here you get this is so this is of the form u prime times v plus uv prime. Okay, so this is the ddx of x squared times 1. Okay, so this is sine 3x. All right. So we integrate. When you integrate, you get integration of sine 3x uh, negative 1/3 cosine. Okay, plus c. Okay, constant. Okay, so you have a solutions now. Not really explicit, but these are solutions anyway. So x uh, let's see, y is negative 1 over 3x squared cosine 3x plus c over. Okay, so this is what we call a general solutions. Why we call it general solutions? Because it's still containing the unknown c here. So that's the reason we call it general solutions. When we plug in a data to find a c, then it's called particular solutions. Okay, so let's see if there is a solve this one. Okay, suppose when x equals 0, x cannot be 0. Yeah. All right, so let's just make up some data. Suppose given data, data is given. Say y1 is, let's see, say this is 1. Okay, so what we have here, so substitutions give you 1 over 3 cosine 3x cosine 3 plus c over 1 is 1. Okay, so you get c is 1 minus 1 plus. Okay, so here we have the solution satisfying the data is this one. Y p is, I can say it outside. We have c here is minus 1/3 cosine 3x. Okay, this is called a particular solutions. So that's the trick of doing what do you call it? integration factor. Okay, let's do some more example. One more. This. And see. One more problem and then one more. We skip the electric circuit here, Kirchhoff law. We'll just see kind of fluid brine. Okay, let's do one more example on, for example, this one. Let's propagate. Let's try to recognize the P and Q. So this is the P. So this is the Q. Okay. All right. So let's integration factor. E within x plus 1 x. Okay, so integral of 2. This is just 2 ln of x plus 1 plus c. All right. So you assume that this is ln x plus 1 square, right? And the c assume 0. So this is the easiest one. So our integration factor is e to the ln of x plus 1 squared, which is x plus 1 squared. Okay, so you multiply by integration factor. Okay, so we get y prime x plus 1 squared plus let's see, what is this? Times this is, okay, so 2x plus 1. Here you have x plus 1 cube and then multiply by square power 5. But here we can recognize this as the PDX of multiplications, the product y and x plus 1 squared. Okay. Yeah. So then integrate. So you have y x plus 1 squared equation of. Okay. So this is the substitution method. U equals x plus 1, du equals dx. Okay. So you get 1 over 6 x plus 1 plus b. Now, c here is we don't substitute c. We don't assume c equals 0. So just keep it c. So what we have now is, well, let's see. So y equals divided by x plus 1 square. So 1/6 x plus 1 power 6 power 2 is power 4 c over x plus 1 square. Okay, so this is a general solutions. All right, so the problem only asks for general solutions, not the particular solutions. Okay. All right. One example of the word problems now. So how do you do this type of problem? All right, so let's pick up a problem 16. Okay. Okay, so this is the problem. A tank initially contains 200 gallons of brine, so that's salt water, with 50 pounds of salt in solutions. Okay, so that gives you concentrations. So concentration is 50 over 100. So 1/4 pound per gallon. Okay. Let's see, a brine containing 2 pounds salt per gallon entering the tank at the rate of 4 gallons per minute. Okay. And at the same time, at the same rate, it's flowing out. The mixture of the tank is kept uniform by constant stirring. Okay. Let's see, let's get some picture of this. We really need, so this is a tank. So see, this about this one. So 200 gallons of brine with 53 pounds of salt. That's the concentrations, initial concentrations. So what happened next is that you let a brine flow into the, so a brine flows in, okay, and then at the same time you let it flows out. Entering the tank at the rate 4 gallons per minute. Okay. This flowed also 4 gallons per minute. Same as flow. So that's why the sorry, because the flow in equals to flow out, then the amount of the brine inside the tank is remain the same. Okay. volume of brine in the tank remains the same since flow in equals flow out. Okay, so there's a device here. So it keeps the concentrations constant. Sorry, keeps the concentration homogeneous, not constant, uniform, and constant steering. Okay, find the amount of salt in the tank at the end of 40 minutes. Okay, so how we do this problem? Okay, so let's say um, how we do formulate this type of problems. All right, so let's decide on what you want to compute at the moment. Are we going to compute the amount of salt or concentrations? Okay? Because the concentration is just the amount of salt divided by the volumes. Okay, so you can do, for example, on the say amount of salt. Okay, so let's say that A times D is this amount of salt in the tank at time t. So this is the first step. You decide. Okay, so what happened amount tank t? In the beginning, before there is a flow in and flow out, in the beginning contains 200 gallons of brine with 50 pounds salt per solutions. Okay, so you have a say this 50 pounds of salt. Okay, so A0 is 50. This initial data. And what else we know? Okay, what is flows in? Flow in is 2 pounds salt per gallon at the rate of 5 gallons per minute. So how much salt flows into the tank? So 2 pounds per gallon and 4 gallons per minute. Okay, so you have what multiply 8 pounds per minute means this is the rate in, the rate of the flowing in. Okay, what about the flowing out? Uh, okay, so what's the flow out? Flow out is the say same 4 gallon per minute times the concentrations. Concentrations in the tank. So what is the concentrations? Concentrations is nothing but the amount of salt defined by the volume. Okay. So we have here flows out is 4 times A, so plus 450 uh, pound per minute. Sorry. This is flows out. This is out. This is in. Okay, so coming in is 8 pound per minute, and flows out is A over 50 pound per minute. Okay, so how can we compute? What's the law of this dynamics? Okay, so the law of the dynamic is this. Is this one, the rate of change is difference between flow in and flow out, right? So in this case would be the A dt, right? The flows in is this 8 minus that flows out is A over 50. Okay, and the initial data is given, right? So solve for A. And the question is find the amount solved at the end of 40 minutes. So A 40. A and A 40. Okay, so we have this one now. Let's see how to solve this one here. Actually, this is still separable, right? So you don't have an integration factor. But this is still separable. Why? Because you can remove this one here, left hand side, and move the t here. And then you still have uh, you solve this without integration factor. This is separable because the A over is so we can solve this one here. Okay, change is okay. Solve this one. How to solve this one here? Okay, so if you take 50 out, you get this is 400. Oh, is that right? Yes. minus 8 of 50. So this becomes 50 dA over. And if we solve this one, so 50, let's see, okay. So what we have here is that A, well, assuming A is more than 400, let's see, what happened here for 8, 8, let's see, okay. So what's the concentration in the, in, how, this is, okay. So assuming this is positive, let's assume, okay. So then we get 400 minus A is something like this. So exponential, apply exponential to get exponential, cancel the ln. Oh, sorry. This 50, right? So this 50 becomes the power. So T, let's see, okay, this one. All right. And this 50 is cumbersome. Let's see how we deal with this. Equation. Let's see. Yes, P over 50 plus C, so like this. And so we have take exponential e to the, say this is C tilde e to the P over 50. Okay, so A here is A of T. Take S out, so 400 minus e to the T over 50 C. All right, there we go. Okay, and then we'll try to find out the C prime. What's the initial data? What's initial data? A now is, say, what is A? 50. Okay, so plugged it in. So 400 minus, so A equals 0, that's 0, that's C prime. So that's 50. All right, so that tells you C tilde is 350. All right, so then we get the uh, the equations now. So it is 400 minus 350 e to the t over 50. Okay, so then the last question is this. Find the amount of salt at the end of 40 minutes. Okay, so let's plug in 40. And so this is what's called the general solutions. Oh no, this is particular solutions. This is general solutions. This particular solution. A40 is 50 e to the 4. Okay. Can you compute this one?
The answer that I got is minus 378.9.
Minus 300. Let's see, what's this minus 300? Can be minus though. Really minus because this e to the 4/5, e to the 1 is 2 something. Let's see. There's something wrong here. Let me check again. The positive, right? Because the amount of salt. All right. So, but I'll check again the computations. Where was wrong goes wrong? Where it went wrong? Okay. We'll stop here and then I just share the notes. Later, I try to find some mistake here. Okay, I'll see you then next Monday, and the joint quiz will be on Monday at the time for the problem sessions. Okay, I'll see you then later. Take care.
Okay, take care, sir.
Thank you,
For
Pak.
today.
Yes, sir. See you next
Okay.
week.
Thank you, sir.
Sir, sorry.
Yes,
I
uh-huh.
think I